This is video 2 of matrix representation. In this video, we're going to define the link adjacency matrix for a network. We're going to define the Laplacian matrix and the normalized Laplacian matrix for a network. First, the incidence matrix is used to help us construct the link adjacency matrix. In B, we have the incidence matrix for the network below. Recall, the incidence matrix is the matrix whose rows represent the vertices or the nodes, and whose columns represent the links or the edges. Given the incidence matrix for a network, we can define its transpose. The transpose of a matrix is the matrix obtained whose columns are the respective rows of the original matrix. So, for example, if we look at the matrix B and we see the first row is 1, 0, 1, 0, 0, then in the transpose, the first column is 1, 0, 1, 0, 0. So each row becomes a column in the transpose. The link adjacency matrix is the square matrix obtained by the formula the incidence matrix transpose times the incidence matrix minus twice the identity. So we'll be subtracting 2 down the diagonal once we find this product. So what we're after is we're using the incidence matrix to obtain the link adjacency matrix. Now, what is the link adjacency matrix? Recall that two links are adjacent if they share a common node. So, link A is incident to links B and C. So we'll find the matrix that records this information, the link adjacency matrix. First, we find the product of the incidence matrix transpose times the incidence matrix. Given that we found the transpose, the matrix multiplication is compatible. So once we find this product, the incidence matrix transpose times the incidence matrix, you will see that you have 2's down the diagonal. That's because at each diagonal position we wind up adding 1 plus 1. So that's the reason we have minus 2 times the identity. That gives us 0's down the diagonal without changing the rest of the matrix. So the matrix that we now have is the incidence matrix times its transpose without the 2's on the diagonal. And let's see what that result is. We said earlier, if you look at link A, that link A is adjacent to links B and C. So the link adjacency matrix in row A should have 2 1's in positions 2 and 3 that represent B and C respectively, and it does. Notice that link B is only adjacent to link A, and there is a 1 in the first column of row 2, representing that adjacency. So we have node adjacency, and now we have link adjacency. Now, we mentioned that we would be using the degree matrix for other values or quantities of a network. So we're going to use the degree matrix for our next formula. Just to make sure we recall, the degree matrix is the square matrix with zeros everywhere except on the diagonal, and then we have the respective degree of each node on the diagonal position. The Laplacian matrix is defined to be the degree matrix minus the adjacency matrix. So that results in having the degrees down the diagonal, and we have a -1 where there is a corresponding adjacency. So it's the degree matrix minus the adjacency matrix. Using the Laplacian matrix, we now want to define the normalized Laplacian matrix. In the normalized Laplacian matrix, all of the entries will be from -1 to +1. Looking at the equation below, we can in fact use the degree matrix again. The resulting equation gives us this definition for the normalized Laplacian matrix, which is often used as the definition of the Laplacian matrix. So if I is equal to j, in other words, if we're on the diagonal, the entry is 1, so long as the degree is not 0. So if we don't have any isolated vertices, the entry is 1. If we're not on the diagonal, if we're in position I, j, where node I is adjacent to node j, then we use the product of their respective degrees and find the square root of that. That is the denominator of our entry, and then we have the negative of the fraction 1 over this product. Otherwise, we have a 0. So let's look at an example. Going back to this one, we have 1's down the diagonal. We have no isolated vertices. And let's see, what would we have in the first row, second column? The first vertex, or node 1, is adjacent to node 2, so it's not 0. The degrees of each of these are 1 and 2, respectively. So what does the formula give us? In particular, the formula was -1 over the square root of the product of their degrees. Since their degrees are 1 and 2 respectively, the product is 2, and so the entry in this position is -1 over the square root of 2. We will have zeros elsewhere because this is the only adjacency for node 1. Since there are 7 links in the network, we will see that there are 6 additional non-zero entries in the matrix below. So in this video, we introduced the idea of link adjacency. We already had node adjacency, but now we also have link adjacency and the corresponding matrix for that. The Laplacian matrix and the normalized Laplacian matrix. These definitions are provided in your book on pages 36, 38, and 39. You might notice that we are skipping around somewhat, and that's because